All right, I know there's some more folks trickling in, but let's go ahead and get started. Thanks everyone for coming to my talk. I'm Colin. This is Slippery SOAP, or Edge Cases in the Same Origin Policy. So we'll start with who am I? I'm Colin Berman. I'm a pen tester on Capital One's offensive security team, mostly specializing in web, cloud, and crypto. I am a Virginia native, born and raised, but just moved out to Seattle, Washington not too long ago. But enough of that, that's me. Now, why are you here? Yes, I know we have one track this year, but just so you know what we're getting into. Essentially, we're going to start by looking at this question: why doesn't the same origin policy protect us against cross-site request forgery? So we'll start with that, and I just want to highlight we're not talking about CORS here. We're going to be talking about the vanilla same origin policy. But we're going to be deep diving into the boundaries of the same origin policy, trying to understand the edge cases of this. So if you're a pen tester like me, hopefully you can walk away with a more complete understanding of where the same origin policy steps in and blocks your attack. Maybe you can find just one more link you can put into your attack chain to get that cross-site attack working. And on the other hand, if you're a defender, no judgment, but maybe you can walk away with some additional mitigations to add some more layers of defense and depth, help protect more against cross-site attacks. Most of this work is not mine. I've collected other people's amazing research, collated it into a reference, so each of these topics we're going to be talking about today could probably be its own talk. We're going to go wide and shallow, but at the end, we'll be walking away with a bonus vulnerability that I get to disclose. So I'm super excited. Let's get into it. And we're going to start off with the same origin policy. Now, the fine folks at Mozilla define this as the same origin policy controls interactions between two different origins. And this definition now gives us two more things we're going to have to define. So what's a cross-site interaction? It's going to be one of three things. We're going to be looking at cross-site reads, writes, and resource embeddings. And when we say origin, specifically, this means it's going to be comprised of three components. We've got the protocol, probably HTTP or HTTPS, the host name, and the port. Usually no one sees the port if it's just a default. But if any one of these three things change, that's going to give us a different origin. For example, if we're making a request from http://example.com to https://example.com, even though they have the same host name, that's treated as a cross-site request. So let's get into it. We'll start off with cross-site reads, but before we look at cross-site reads, let's look at same-site reads. For my example here, I'm looking at example.com, since I'm allowed to pull this up as an example. And in my browser, I've opened up the developer console at the bottom. This allows us to run JavaScript in the context of example.com here. We're going to be seeing a lot of pictures like this in the next few slides, but what's happening in this first one here is my JavaScript is attempting to read content from the same domain. So I'm on example.com, I'm reading from example.com, and that goes through fine. Makes a lot of sense. One site should probably be allowed to read content from itself. But now we can contrast this with a cross-site read, which we look at the bottom, we don't have to read the code, but we get these three big red error messages at the bottom. That attempt to read cross-sites, so I'm on example.com, but it's trying to read content on gmail.com, that gets blocked. I mean, can you imagine if that were allowed? This would be a whole new OWASP top 10 vulnerability, where if you accidentally browse to a malicious website, it can now read your data on any other website. So maybe as a pen tester, I should be sad, but I'm kind of happy that this gets blocked. So that's cross-site reads blocked by the same origin policy. Let's look at something that's now allowed, so cross-site embeds. Still on example.com, but I've embedded some content from gmail.com, and this goes through fine. This is also kind of how the internet works. We need to be able to embed content cross-domains. But again, this is not a cross-site read, so the JavaScript or the web server itself does not have access to view the contents of this image. It can get some metadata, like the dimensions of the image. If we were embedding a video, JavaScript would be able to see the duration. And it's not just media. We could also look at embedding style sheets or even a script from another domain. and that's all allowed by the same origin policy. So we had cross-site embeds, which are allowed. We had cross-site reads, which are blocked. Something in between now, cross-site writes. What does this even mean? Well, the simplest example is just clicking on a link to take you from one site to another. It's how the internet works, right? Internet needs to be open. We need to be able to link between different websites. So this kind of cross-site write has to be allowed. But it's not just when the user clicks on a link themselves. We can also think about when the web server sends someone to another website automatically with a redirect. We can also send some data along with that request with a form submission. And it's not just HTML forms, but also JavaScript APIs. There's a variety of these. Most common used to be XML HTTP request. Now we have the more modern fetch. But essentially, there's a bunch of ways to send information from one website to another in JavaScript. This might seem like it's nice to be able to send that information, but this is also known as cross-site request forgery, when we're sending a payload from one domain to another. What might that look like? How do we exploit this? So now I've switched to a different kind of example, but again, we're going to be seeing a lot of pictures that look just like this in the coming few slides. Cross-site request forgery is an attack targeting a victim user and their web browser. And it starts off when the victim user browses to our malicious website. So in this slide, we're going to be the hacker. I hope that's OK with everyone. But when the user browses to our malicious website, we can use JavaScript to tell the victim's browser to make a post request over to, let's say, example.com/change email. And now this cross-site request forgery attack will successfully change the victim's email address on example.com to our malicious email, attacker@evil.com, let's say. And this is allowed by the same origin policy. For the exact same reason we need to be able to click a link from one website to another, apparently we need to be able to send post requests initiated by a malicious domain over to a legitimate site. And of course, there's great ways to protect this. I think the most common and the most robust is called cross-site request forgery tokens, but we're not talking about that. Let's instead look at what kind of cross-site request forgery attacks are even possible. So we'll go find also, forgot to call out, but when the victim's web browser makes that cross-site post request, the web browser automatically attaches the cookie that the user has. So if they're logged into this example.com, when evil.com tells the web browser to make that post request over, it automatically attaches the cookie as well. That's the internet for you. So what's possible here? Let's deep dive into the same origin policy here. So when we're using the fetch API to make cross-site requests, this is approximately going to be limited to what we can do with an HTML form. We're going to see the same types of things where we can only make a get, post, or head request, meaning no cross-site deletes or patches or puts. Again, we're not talking about CORS. CORS changes everything. But by default, we can only send these 3 requests, and we can only modify a few different headers. The most important one being content type can only be either form data or just plain data. So importantly, defenders take note, JSON is not a valid content type for cross-site requests. How can we use this to our advantage? Well, as we're designing our APIs, if we make sure all of our APIs are only accepting JSON content, and if we are strictly validating the content type header on these requests, then we know cross-site requests coming from evil.com can only have one of these 3 different content types. And unless we implement CORS, those cross-site requests will never be able to add that JSON content type. Similarly, since these are the only safe request headers allowed on these cross-site requests, if all of our APIs expect to see something like x-example header, cross-site requests cannot include that. And I'm not saying this should be your only protection against cross-site request forgery. A lot could go wrong. You might not be validating the content type exactly correctly. Like what if I say text plain semicolon JSON? But it can be an effective mitigation to add an additional layer of defense in depth. Help protect against cross-site request forgery if your more robust CSRF tokens do fail for some reason. So that is the same origin policy by default. I've said it a few times, but there are ways the same origin policy can be weakened. For example, if you see a site implementing CORS, sending CORS headers, all bets are off. And that first vulnerability, the hypothetical vulnerability we talked about at the beginning, cross-site reads, now becomes possible. So if your website implements CORS, you might be opening yourself up to users browsing to evil.com and losing their data. Similarly, we can do something in JavaScript by setting the document.domain variable to a superdomain, and this opens up the same origin policy to allow additional cross-site requests from other subdomains of that superdomain. So this can be especially dangerous if you have a ton of different subdomains. Some of them you treat as business critical, extra secure. Some of them maybe you don't worry about. But if you get cross-site scripting on one of those other subdomains, then your more critical applications can open themselves up to these risks by setting document.domain. Whew, okay. That's the same origin policy. Let's now go look at how this differs for the same origin policy for cookies. Just to recap on cookies, what's a cookie? When a user logs into our website, we can tell the browser to save this cookie, and that cookie will then be sent along with every subsequent request to our website. But which websites will that be sent to? So let's look at the same origin policy for cookies. And I've done my best here to come up with a one-to-one correspondence between the cookies and the fetch same origin policy. It's not quite exact, but let's see what we can pull out of here. So we said with the same origin policy, that origin is defined in terms of the protocol, the host name, and the port. Here, instead of scheme, cookies allow us to set a Boolean true-false flag. It's called secure. It basically says, should this cookie be allowed to be sent to non-HTTPS websites? Just HTTP. Not too much configuration room there, just a Boolean flag. On the other hand, the domain attribute on cookies gives us a lot more flexibility. It's a lot like that document.domain variable we just saw, but because there's so much flexibility, we're going to need some more slides to look at that. Finally, instead of port, we have nothing. Cookies provide no way to enforce isolation based on different ports. And we'll take a look at an example of what that might mean in a security context. But that's not where cookies stop. We also have this attribute called HTTP only, which might be a mitigation against cross-site scripting attacks. Basically, it says JavaScript is not allowed to access this cookie. We also have the path variable, which has no analog in the normal same origin policy. Kind of like domain, it's going to say only send this cookie if we're accessing a URL that starts with that path. And finally, we have this somewhat newer attribute called same site, just from a few years ago. This one's really powerful, especially when it comes to blocking cross-site request forgery attacks. So we'll definitely deep dive into that. We'll start with domain, look briefly at port, and then go look at same site. So starting with domain, I've made up this example subdomain tree for example.com. In reality, we only see www.example.com, but let's pretend we also have a blog with public and private components. Maybe there's also a separate development subdomain. And as a first example, let's say we have a cookie that gets set when the user visits public.blog.example.com, and now we want to share this as well when the user visits private blog, example.com. So how can we implement this using cookie attributes? We can do this by setting at the top domain equals blog.example.com. And this ensures that the web browser is going to send that cookie with every subsequent request, not just to the domain that set it, public blog, but also to any subdomain of blog.example.com, including blog itself. So even though we were just trying to share the cookie between these two different blog subdomains, we're also intentionally sharing it with blog.example.com. Now, second example, let's say blog sets the cookie, but we want to share it, let's say, with example.com. The only way to implement this, if we set domain equals example.com, this blows the whole thing up. Now every single subdomain of example.com gets that cookie. We'll take a look at how this matters in a security perspective, but first, just as a more complete picture, here are the different types of isolation that we can actually enforce using that domain property. This is all we get. Anything else is not going to be possible. But why does this matter for us hackers? On this slide, let's be the hacker. Let's say we've somehow achieved subdomain takeover on subdomain.example.com. Maybe there is a dangling DNS record. We were able to claim it. Maybe we just have cross-site scripting on that subdomain. What can we do with that? After the victim user browses to the legitimate app.example.com, logs in, gets that cookie, what happens if that user then browses to our subdomain? Nothing. That cookie will not be sent. That's because by default, the cookie is set only on the site that set it. So navigating to other subdomains doesn't cause that cookie to be sent. Maybe we could do something else with the subdomain. Maybe we could do some phishing since a user trusts the superdomain. But in this case, we can't steal the cookie. On the other hand, like we just saw, if that cookie is instead set with the domain equals example.com attribute, now this attack can go through. Because we have subdomain takeover, we can steal that cookie. And if we manage to steal a session cookie, this effectively gives us full account takeover on the victim user. We can steal that cookie, send it back to the website ourselves. That website thinks we're that user. How did we achieve this? We did it because the domain was scoped to the parent domain and because we had some form of subdomain takeover. That's probably a win for the attackers in here. Don't worry, I got a win for the defenders on the next slide, but first let's switch things up. Let's say first the user browses to our malicious subdomain. What we can do now is in the response, we can set a cookie in the user's browser. And if we set it with the domain, then that cookie will be sent along with every subsequent request to other subdomains. We can achieve something here called login cross-site request forgery. Basically, we're logging the victim into our account. Definitely not as severe as account takeover, but we could still do something interesting with this. We might think, what if we log the victim into our billing account? If they're thinking that they're in their billing account, they see the bill pop up, maybe they'll add their credit card details to the website, maybe they'll pay off their bill. Again, not as severe as account takeover, but there's an interesting way to prevent this attack using something called this prefix. So if our session cookie has a name starting with __ host dash, then the web browser will not allow that cookie to be set with the domain attribute. So the subdomain can't scope it to the parent domain. It'll just be denied by the browser. And this works as long as our application was only on this one other billing example.com, if billing sets the cookie and billing reads the cookie. I don't know about you. I've never actually seen someone implement this in practice, but could be a good way to get some additional defense in depth. So that's the domain attribute. Next up, quick slide on the port. We just talked about subdomain takeover. What if there was such a thing as subport takeover? Let's say now as an attacker, we're able to run a server on some other port on the same hostname. Well, there's no way to prevent this, but if the attacker visits our subport, we're going to get that cookie. There's nothing that can be set in terms of cookie attributes to provide isolation between different ports. I guess as the defender, just don't let hackers run web servers on different ports. I guess also don't design your application for this to be a part of its functionality. But something interesting, and we'll come back to this in a little bit. Finally, we're going to look at the same site attribute. And before we talk about same site from a security perspective, let's just explain why this isn't the default behavior or the only option for cookies. I'm going to start with an example that's not about security. So when I say facebook.com, don't worry, I'm not dropping a vulnerability in Facebook. But Facebook has that pervasive like button. Sites across the internet can embed that like button. And so as an example here, Facebook's the green website, and we've got these yellow, purple, and blue websites all embedding that like button. When the user visits, let's say, the yellow website, their browser also has to fetch that like button, and that request ends up sending this third-party cookie associated with Facebook. So the yellow site doesn't get the Facebook cookie, but Facebook gets the Facebook cookie, even though that request initially came from the yellow site. It's called a third-party cookie, and we have a way to disable this functionality using the same site attribute. That behavior we just saw is called none, same site equals none. It means send that cookie along with cross-site requests. Don't worry about it. Maybe only set that if you're doing tracking or analytics. On the other hand, we've got this property called SameSite equals lax, which will ensure that the cookie is only sent when we navigate directly to that website. So if we're just fetching content embedded in the yellow site, then we don't send the green cookie, only send the green cookie when we browse to the green website. Finally, SameSite equals lax says only send that cookie when we follow a link from the green website to itself. But lax and strict, we're not going to get so much into. Let's talk just about none versus yes. So we'll start with none, and this is what we saw before, where if we are conducting a cross-site request forgery attack, even though the request is initiated from our malicious website, going to this other example.com, the web browser will happily include that authentication material in the session cookie, send it over. This request to change the user's email to the attacker's email address gets implemented. On the other hand, if this session cookie is set with SameSite equals lax or strict, that cookie no longer gets sent. This is treated as a cross-site request since it originated from a different domain. Meaning, SameSite attribute can be an effective additional mitigation to protect against cross-site request forgery. It's not a silver bullet. Like I said, SameSite's only a few years old. So if you still have legacy users on a legacy browser, then their browsers may not implement this attribute. It's something to add in addition to cross-site request forgery tokens, but it can be an effective layer of defense in depth. That being said, if we go back to subdomain takeover, so on the previous slide, this was the user browsing to our malicious website, evil.com. SameSite blocked the CSRF attack. On the other hand, if we have subdomain takeover, the SameSite specification treats the subdomain as the same origin. So this will be a SameSite request. Even though it's a different host name, that SameSite cookie is going to be sent along with that cross-site request forgery request. So if we've got even just cross-site scripting on a subdomain, we can now achieve cross-site request forgery. So again, SameSite is not a sole provider of protection against cross-site request forgery, still an effective layer of defense in depth. Now, because SameSite's so new, with any new implementation, we're going to see some security bugs. Fortunately, these have all been fixed. Maybe if you're a pen tester, you're sad about that, but I kind of like to see bugs get fixed every now and then. But when it was first being developed, SameSite had a few ways you could bypass this property. And again, these are all fixed. I'm just trying to show that whenever we introduce a new browser technology, there might be good ways we can exploit that. So when SameSite first came out, still in the alpha stages, you could send that SameSite cookie on cross-site requests, for example, by clicking a link within an iframe, or turning a page into reader mode and then making that request. But again, these are all fixed now. Some things that haven't been fixed, some weird browser quirks. In Firefox, if you drag a URL from one website into your address bar, and it sends you over to another website, that's the SameSite request. Even though it's from two different websites, that SameSite cookie will still be sent. And it seems like they don't really have plans to address that, not really treating it as a security issue. If you can exploit it, though, maybe go buy that researcher a coffee. And I know Internet Explorer was just sunsetted yesterday, pour one out, but we can still make fun of it, right? So Internet Explorer, in classic Microsoft fashion, has redefined the standard and said ports don't have any place in the origin. So that example we saw before with cookies not respecting port-based isolation can happen with the same origin policy in general. If your users use IE, that can open you up to these cross-origin reads and maybe even more nuanced cross-site request forgery attacks. But it's not just IE. We also have Chromium-based Edge, which allows cross-domain reading of applied CSS style sheet rules. It's a mouthful. What does that mean? Well, maybe if we're a hacker and a user on Edge browses to our website, we can read the CSS rules that are applied to that other website, which might change, for example, depending on whether or not the user is logged in. So against Edge users, this can provide a way to detect whether or not a user is logged in on another website, maybe for further targeting. I just think it's kind of funny that Edge has to change everything. Anyway, that's cookies. Going to move on to our third and final topic. So we're looking at DNS rebinding. which I want in this presentation to view as a gap in the same origin policy. We said the origin is defined in terms of 3 components: protocol, host, port. Importantly, what is not included in that definition is what the host name resolves to. The host name is a part of the origin, but if we switch that to resolve to something else, that's fine. Different website, same origin. What does this look like? I've got 2 browsers here. On the left browser, I've navigated to this website, what's it called? Rebinder.nofetch. And at the time of browsing, this record pointed to my infrastructure. It's pointing to my public server out there, and we get the attacker website. Now on the right side, same exact URL, but after navigating to the page, the host name was rebound to localhost. So on one side, we have this public server. On the other side, we have a local file server that's only bound to localhost. Obviously 2 different websites, but under the same origin policy, these are the exact same origin. So we can achieve cross-site reads same-site reads from one to the other. Let's take a look at how we might exploit this. In this example, the victim user has browsed to my malicious web server. After they landed on that page, I'm running JavaScript. I've then rebound that host name to point to localhost. And after that propagates through the internet series of tubes, if I let that settle, I can now make same-site requests to the exact same URL, but now all of a sudden my attacker infrastructure, JavaScript running on my page, can read the contents of the local file server. In this case, it's only possible in Firefox. While I was making these slides, I noticed Chrome had recently introduced a new specification called private network access, which effectively adds the IP address we're resolving to the definition of the origin. So same exact attack I'm trying here, but we get, again, these 3 big red JavaScript errors at the bottom. So let's blow those up. Chrome says there's 2 reasons we're not going to allow this request through. 1, it was not in a secure context, meaning the sites were on our HTTP. 2, and this is the rub, the resource is in a more private address space local. Meaning when we first browsed to the website, that was a public IP address. Now we're trying to retrieve this local host, 127.0.0.1. Chrome can block that. It detected the DNS rebinding attack and put a stop to it. But let's talk about that first bullet point a little bit more. The request was not in a secure context. Why does that matter? What happens if we try the same thing from a secure context? Well, we're going to get this big error popping up. To demonstrate this, I've pointed my subdomain example.nofetch to example.com. And when I try and access that over HTTPS, we get a cert mismatch. So the certificate presented by example.com is signed by a trusted certificate authority. It's installed on my system. Everything looks good, but the host name on it, example.com, doesn't match the site that the user was navigating to, example.nofetch. And yes, we know that users will often click through these warnings, but this warning and the option to click through it only shows up when we're navigating to that page. If we try the same thing with JavaScript, the request is outright blocked. There's no way to click through this and say, yes, I am sure I wanted to do a same-site read over to this secure website with a SSL error. So that's why Chrome and their private network access implementation doesn't care if you do this from a secure context. DNS rebinding just shouldn't be possible in a secure context because of the cert mismatch. So why am I still talking about this? Surely all web browsers fully validate SSL. Well, there's one web browser known to you pen testers out there called Burp Suite, which until recently did not validate SSL at all. And yes, this could open you up to man-in-the-middle attacks, but if you're an internal pen tester at a company, maybe you're on a VPN, and that makes man-in-the-middle attacks harder. Nonetheless, internal pen testers using Burp Suite were still opening their companies up to the risk of DNS rebinding, scraping internal websites. That implemented HTTPS. Fortunately, I reported this over to the great guys at Portswigger. They said, thanks for sending this over, and now we have an option in the latest early adopter version of Burp Suite to enable TLS validation. Now, if we try this same thing, we get this big error, cert mismatch. And this is an early adopter for now, but I'm hoping once it undergoes a little bit more testing, and we're sure it's not breaking too many pen testers' workflows, this will just be on by default. So there we go. I wanted to include a few further topics in case you want to read more at home, but that's that. Let's open it up for Q&A. Yes? So there was a really good article out of Wired a few years ago that demonstrated how often these attacks happen against home devices, Internet of Things, think, maybe even against someone's router. I'm not sure how often they actually get exploited, but a lot of products out there are actually vulnerable to this, probably because a lot of these home Internet of Things devices don't implement SSL. Thanks. Absolutely, thank you. I forget, everyone's so much louder up here. But Chris was asking, how often do these DNS rebinding attacks happen in practice? Thanks. Yes?
What other browsers did you test? Just curiosity.
Sure, so the question was, what other browsers did I test for this? I was initially looking into this when I saw a recent CVE for Zap. Zap had a CVE filed for they didn't validate SSL, and they fixed that. So I figured, why not look at Burp? Burp's bug bounty program specifically called out in their policy, we don't validate SSL. And if you tell us about it, we know that. That's a design decision. We want to make it interoperable. But still, they hadn't thought about this edge case, so they were able to fix that. Besides that, all of the major web browsers are going to fully validate SSL. Thank you. Anyone else? Yes? Yeah, great question. We could have another talk just on this. So the question was, how did the DNS rebinding work? How did that DNS record change over between when the victim first visited the website and by the time my JavaScript made that same site request? So in this case, just for testing, I was just flipping over the domain name in my Route 53 records, doing it manually by myself. When I've exploited this in the past, I have a hook on the website. So as soon as the browser lands on there, I've got API calls set up to automatically switch over the domain name. There's a lot of great tooling out there if you want to conduct your own DNS rebindings attacks, where you can have it, for example, alternate between the two different sites that you're trying to hit. So that when the user first browses to the website, they get your attacker infrastructure. Second time they resolve that, it resolves to the local host, for example. But great question, thank you. Yeah, please. Thank you for the question. I'm definitely not here to talk about Capital One. So they're not affiliated with the talk, but yeah, the question was, suppose we've got a company out there and we're giving developers access to do things with subdomains. I would say that definitely introduces a possibility for insider threat, either intentional or maybe accidental. But like I said earlier, if we've got cross-site scripting on some subdomain we don't care about, that opens up all of these different attacks that we don't normally see. So if that's accidentally misconfigured, maybe someone finds it, exploits it. If it's intentionally misconfigured, giving developers access to create their own subdomains can definitely lead to security issues. Thanks. Any other questions? Yes. So the question was, did I try this out with a wildcard cert? Right? On this previous site, we saw I'm getting the error because the web server example.com is offering up a certificate that doesn't match my host name. And that's what would be blocking it. So we have to think about the certificate on the target site. If the target site has a wildcard certificate, then we could get this attack to work if we have a subdomain of that wildcarded cert. Again, you can't have a certificate for asterisk.com, but if we've got a wildcard, let's say star.example.com, and if we get subdomain takeover, then yes, we could perform DNS rebinding attacks on other subdomains, even if they implement SSL. Thank you. Other questions? All right, well, one more. Sorry, can you say that again? How does this apply to iframes? Great question. Let's look at a few different slides. One, we saw that because iframes implement things a little bit differently, we can see bugs show up in iframes when they don't show up in other contexts. So it's one more edge case to look at. But I would say the most common way iframes are going to show up here is when we go back all the way to resource embedding, which we said was allowed by the same origin policy. Wow, we're really going back, sorry. So same origin embeds are allowed by the same origin policy. That's specifically what allows us to frame another website on our website. And from there, we can try all different kinds of attacks, but iframing itself is allowed. Does that answer your question? Thanks. Last call. Any other questions?
How long did it take you to do all this research? A period of months, or?
I would say period of months. I would also just call out that in developing these slides, every new slide I add, I have to go do more research. So that's how we got to here today. But happy to field any other questions after this talk. I'll just step down. But any other questions? Great, thanks again.